Okay, so in the last video, we defined homology groups. Remember, we defined HKX is ZKX mod BKX, where ZKX is the kernel of the differential from CKX to CK minus 1x. And BKX is the image of the differential from CK plus 1x to CKX. Okay, so both of these are subgroups of CKX. And the key fact that d squared is 0 implies that BKX is contained in ZKX, so it's meaningful to form this quotient. Now, there's not very many cases where we can say anything useful just sort of directly from the definitions. There are a couple of cases, and that's what we'll do in this video. So this proposition, first thing we can say is suppose X is a finite set with discrete topology. Just a finite set of separated points. So then the claim is that H0x is just the free abelian group on X, a set of formal Z-linear combinations of points of X, and HKX is 0 for K different from 0. Okay. So let's prove that. So let's let CKA from delta K to X be so for every point A and X, we've got a constant map from delta K into X, which sends everything to A. And it's kind of clear, because we've got the discrete topology on X, that any continuous map from delta K into X has got to be constant. So every continuous U from delta K to X is constant. Therefore, SKX, the set of continuous maps, that's just equal to the set of all these CKAs. And so the chain group CKX is just the free abelian group generated by these guys. Okay, so that's what the chain groups are, and now we need to understand the differential. So if we look at this CKA composed with delta I, so that's a map from delta K minus 1 to X. Well, that's, of course, I mean, that's, you just take a constant map and compose it with something, it's still constant, right? This is just CK minus 1A. Okay. So if we take the boundary of CKA, so that's sum from I 0 to K minus 1 to the I, and then you've got these composite here, which is CK minus 1A. Okay, so it's all just all the same map. You just got all these plus or minus signs. So this is 1 minus 1 plus 1 times CKA. So KK minus 1A. Okay. And so what happens? These terms are cancelling in pairs, but it depends what K is, right? If if K is odd, then you've because you've got in the 0 here. If K is odd, then you've actually got an even number of terms, plus or minus 1 alternating, and they all cancel. But if k is even, then, because you've got in the zero term, you've got the zero term, which is just this ck minus 1a, and then the remaining terms, there's an even number of them, alternating plus or minus, and they all cancel out. So you get ck minus 1a. Okay, so if we look at these all these chain groups, then in degree zero, the zeroth chain group, you've got a free abelian group on X. So this here, when I said it's the free abelian group generated by these CK, but this, because these constant maps sort of biject with the elements of X, this is essentially just we can just identify this with the free abelian group on X, right? Identifying point with the corresponding constant map. Okay, so this is you got this. So this is in degree zero, and then in degree one, again we've got the same zx, but now this is a d on d on c1, which is just zero. So this map here is zero, and now this. And so this is degree 2, this is degree 3, and by what we wrote up here, this from degree 2 to degree 1, we're sending ckA to ck minus 1a. So this is essentially just the identity, whereas this is 0, etc. Okay, so from this we can see what the z's and d's are. So what's the zkx? That's your kernel. Okay, so the kernel of the map here. So we're so often this is going to be the whole thing, right? I mean, this is the whole of whole free abelian group on X. Well, firstly, if k is 0, then you've just got nothing. Or if k is odd and positive, in these like in case 1 and 3 and so and 5 and so on, you've got the 0 map coming out. So the kernel of the 0 map is the whole group. So this is and so that's what we've got if k is 0 or k is odd and positive. But in other cases, right, if k is even, right, like k is 2, here you've basically got the identity map. The kernel, remember, that's the stuff that gets sent to 0. The only thing that gets sent to 0 here is 0. So and the same, the map from 4 to 3, that's just the identity map. So the kernel of that is trivial. And also, of course, down here in the negative groups, it's also got to be trivial. So that's what we get otherwise. Okay. And then what about bkx? Okay, so that's the image of the differential. So here, if we look in degree 1, right, you're looking at the image of this map here, but this map's just the identity, so you get everything. And similarly, here you've got your Z3, the next group, you've got the identity coming in to this group in degree 3. So the image of that is the whole thing. So here we get, in those cases, we get the whole free abelian group on X, and that was like in degree 1 and degree 3 and 5 and so on. So this is if k is strictly positive and odd. But in all other cases, well, of course, down here, your BK groups are 0 just because there's nothing going on. And then in every other case, in the even non-negative cases, the image, the map coming in is 0, so the image is 0. So we can just summarize this picture. you see that we more or less got the same answer in the two cases. Okay, so it's only when k is 0 that these two groups differ. That's the only case where anything's going on. Okay, so here you've got a group zkx mod bkx, but zk and bk are the same, so the quotient group is just trivial. And your h0x, okay, so that's z0x mod b0x. Okay, and then your z0x by this first clause here, that's just the free abelian group on x. And then down here, k is 0 is not one of the exceptional cases for bk. Your b0x is the image of this 0 map here, so that's just trivial. So you just get the free abelian group on x, and that's what the claim was. Okay, so that tells us the homology of a finite discrete space. Okay, so now suppose we've got a space X that isn't discrete. Okay, so what can we say? I mean, we can't really say anything very interesting about the homology groups of k bigger than 0, but we can at least understand reasonably well what h0 is. So the proposition is like this. Any x, well, firstly, let's just record that hkx is 0 for k negative. That's just more or less obvious. And h0x is isomorphic to the free abelian group on the set pi 0x. Let's just recall that's a set of path components. So the quotient of x by the equivalence relation, where sort of x twiddle y means there's a path from x to y. And so some time ago we proved that this is an equivalence relation, relation of having a path from x to y, continuous path. That's an equivalence relation on x. So we can form a set of equivalence classes that's called pi 0x. And then having formed this pi 0x, we can take the free abelian group of formal linear combinations of elements of pi 0x. So that's what we've got on the right-hand side, and on the left-hand side, the zeroth homology. So, so firstly, k less than 0, I have, of course, ckx is trivial, therefore zkx. These are subgroups of ckx, so they're trivial, and therefore hkx is trivial. Okay, so nothing really to say there. Okay, so, okay, so h0x, that's z0 mod b0. So what's z0x? That's the kernel of the differential going from c0x to c minus 1x. Okay, so your z0x is just the whole of c0x, right? They're homomorphism to the 0 group. The kernel has to be just the whole domain. And so h0x is c0x mod b0x. Okay, so how do we understand that? Okay, so to understand this, let's use the following notation. So for A and X, um, C of A is the path component. Okay, so this is an element of pi 0x. So elsewhere we might have denoted this just by square brackets. A was A in square brackets, but those kind of square brackets, they have too many meanings around here. So we're going to use a different notation for the time being. Okay, so now so we're going to extend this linearly. Yeah, so okay, we just we've got this function from x to pi 0x, and we just extend it linearly to get a map from zx to z pi 0x, like so. And I want to claim that C, this extended C, if we apply it to the subgroup B0x, is 0. Okay. So if we've got some U in C1x, well let's say if U is a map from delta 1 to x, then that means that U gives a path from U delta naught, U of E naught to U of E1. So that means that these 2 points, the 2 endpoints, this U from delta 1 is essentially a unit interval. So this is basically, it is a path in X. And these are the endpoints of the path, and they're the same. So that means that C of U of E naught is the same as C of U of E1. And therefore, if we do C of du, well, what's du? So that's d, the boundary of a path is just the difference between the endpoints. That's the definition of d for on one cycles. So this is ue1 minus ue0. Okay, so that's just 0. Okay, because these two things are the same. So therefore, so that's when you do C of du for when u is one of these generators of C1, and therefore we conclude that C of du is 0 for all u in C1x. But these the collection of all these possible du's, that's precisely the definition of B0x. So here we're saying that C of B0x is naught. Okay. So that means we've got a well-defined map C bar from the quotient C naught x mod B naught x, which as we said is H naught x, to Z pi 0x, defined by C bar of a coset, say V plus B naught x, is just C of V. Okay, so we've got this C bar here, and in the opposite direction we can do something kind of rather similar. Okay, so suppose we've got 2 points, A and B, in X. With A related to B, i.e. It means, what does it mean to say that A is related to B? It means that there's just a path U from the unit interval, which we're going to identify with delta 1, to X. U of E0 is A, U of E1 equals B. So endpoints of the path are A and B. Then that means that du, so that's U of E1 minus U E0, is B minus A. So that means that B minus A lies in the so B minus A lies in the subgroup B0x. Therefore, cosets A plus B0x is the same as B plus B0x. So that means we have a well-defined map. Let's call it R, say, from pi 0x to H0x. R of R of some path component CA is just going to be this coset A plus B0x. So we're going to extend this linearly, given N1 up to NR in Z, and let's say P1 up to PR in pi 0x. We put R of this is just going to be N1 R of P1 so we've so now we've got a homomorphism from Z pi 0x to H0x, and this is kind of reasonably easy to see that this is inverse to the map that we had previously. Inverse to C bar. Okay, so yeah, we've and that completes the proof. We've got an isomorphism from this H0 group to the free abelian group on pi 0. I mean, in this, it's kind of a bit fancy to write it all out, but basically, H0x and free abelian group on pi 0x. The definitions are more or less the same, right? You just start with your set X, and you two different things. Firstly, you want to make it into an abelian group by taking linear combinations. But secondly, you want to collapse it down. You want to say that things are the same if there's a path between them. So the definition of H0 and the definition of free abelian group on pi 0, those are just kind of slightly technically different ways of expressing the same idea, but they turn out to be isomorphic.